Hello everyone, I'm Abhishek Dash. Thank you for letting me present our work in NAACL Student Research Workshop 2021. Our work is entitled Emotion Classification in a Resource Constrained Language Using Transformer-Based Approach. Emotion classification is basically the process of computationally identifying emotion from text. The 6 basic types of emotions are joy, sadness, anger, fear, disgust, and surprise. Our main goal is to develop a system that can recognize these 6 basic types of emotions from Bangla text. The system will have the ability to predict a sentence like আজীবন সাজাপ্রাপ্ত দণ্ডপ্রাপ্ত আসামির মতো বড় একা আমি বড় একা, which is in English I am as lonely as a convict sentenced to life in a particular emotion class, in this case which is sadness. The most challenging situation that we faced to begin our research work is the unavailability of benchmark annotated Bengali emotion corpus. We took the challenge and developed our own emotion corpus, which is called BMOC. The corpus contains 6,243 Bengali text documents, and we annotated them with 6 basic emotion classes. Moreover, we investigated the performance of various machine learning and deep neural networks and transformer-based approaches on top of the corpus. And finally, we proposed a benchmark system to classify emotion from Bengali text with the experimental validation on the corpus. The corpus has been developed using data from various sources by 5 human crawlers. They accumulated 6,700 text documents. The raw documents then went through some pre-processing steps like removal of non-Bengali words, punctuations, emoticons, and duplicated data. Data less than 3 words were also discarded to get an unerring emotional context. After pre-processing, the corpus holds 6,523 unlabeled text data. The annotation was done by 5 postgraduate students working on Bangla language processing. The initial labeling was inspected by an NLP expert who discarded some data with neutral emotion or mixed emotions. We evaluated the corpus with coherence kappa and intercoded reliability, and we get 91.3% intercoded reliability and a coherence kappa score of 0.91, which reflects the quality of the corpus. Now at this stage, the corpus holds 6,243 labeled text data. Here is the statistics of our corpus. The sadness class contains the most unique words, which is 7,398, whereas the fear class contains the least. In average, all the class has more than 20 words in each text document. By analyzing the number of text versus length to text distribution, we noticed that most of the data are between 15 to 30 words long. Interestingly, most of the text of disgust class have a length less than 30. The joy and sadness class seem to have almost similar number of texts in all length distribution. For quantitative analysis, the Jagged similarity among the classes has been calculated. We used 200 most frequent words from each emotion class. The anger, disgust, and joy surprise pairs holds the highest similarity score of 0.58 and 0.51 respectively. These scores indicate that more than 50% frequent words are common in this pair of classes. On the other hand, the joy-fear pair has the least similarity index, which clarifies that this pair's frequent words are more distinct than other classes. These similarity issues can substantially affect the emotion classification task. This figure shows an abstract view of the used strategy. Various feature extraction techniques such as TF-IDF, word-to-vec, and fast text are used to train ML and DNN models. For TF-IDF, we used the most frequent 20,000 words and extracted the unigram and bigram features. Word-to-vec and fast text embedding both are trained on skipgram algorithm, and an embedding dimension of 100 is used. In word2vec, window size 7, minimum word count 4, and in fast text, window size 5 and character n-gram of length 5 has been chosen. For machine learning models, logistic regression, random forest, multinomial naive Bayes, and support vector machine has been used using the listed parameters. In DNN models, convolutional neural network, bidirectional LSTM, and the combination of both has been used, and the hyperparameters are listed here. For transformer variants, we have used 3 transformer variants: mbert, banglabert, and XLMR. The hyperparameters are listed here as well. All the hyperparameters mentioned in different models have been chosen empirically. Among ML approaches, logistic regression have achieved the highest F1 score, which is 60.75% than random forest, multinomial Bayes, and support vector machine. Logistic regression also performed well in precision recall and accuracy than other ML models. In DNN, BiLSTM with fasttext outperformed other approaches concerning all the evaluation parameters. It achieved F1 score of 56.94%. However, BiLSTM with fasttext achieved about 4% lower F1 score than the best ML method, which was logistic regression. After employing transformer-based models, it is observed a significant increase in all scores. Among transformer-based models, BanglaBART achieved the lowest of 61.91% F1 score. However, this model outperformed the best ML and DNN approaches. Meanwhile, MBERT shows almost 3% improved F1 score and then BanglaBART. XLMR model shows an immense improvement of about 6% compared to BanglaBART and 5% compared to MBERT. It achieved a F1 score of 69.73%, that is the highest among all models. The confusion matrix illustrates a class-wise proportion to the number of predicted labels. It is observed from the matrix that few data classified wrongly. For example, 8 instances among 71 of the anger class predicted as disgust. In fear class, 6 data out of 83 mistakenly classified as sadness. In the sadness class, misclassification ratio is the highest, which is 15.13%. That means 18 data out of 119 in sadness class misclassified as disgust. Moreover, among 73 data in surprise class, 9 are predicted as sadness. This error analysis reveals that fear class achieved the highest rate of correct classification and surprise gained the lowest. The possible reasons for these incorrect predictions might be or are the class imbalance nature of the corpus. However, the checkered similarity can also be an issue. Few words are used multipurposely in multiple classes. For instance, hate words can be used to express both anger and disgust feelings. Moreover, emotion classification is highly subjective, depends on the individual's perception, and people may contemplate a sentence in many ways. We hope that by developing a balanced dataset with diverse data, incorrect predictions might be reduced to some extent. We compared the performance of XLMR with the existing techniques to assess the effectiveness of our system. We implemented previous techniques on BMOC and reported outcomes in F1 score. The result shows that XLMR outperformed the past techniques with achieving the highest F1 score of 69.73%. There has been a lot of work done on emotion and sentiment analysis in English and other languages, but we have a very poor support in Bangla, as we have lack of dataset and corresponding tools. Therefore, we developed a corpus named BMOC containing 6,243 Bengali text labeled with 6 basic emotion classes. The quality of the dataset was evaluated using the Cohen-Skappa and intercoder reliability. The Cohen-Skappa score was 0.91 and 93.1% intercoder reliability reflects the quality of the corpus. A system is developed that can classify Bangla text into 6 basic emotion classes. Our proposed system obtains maximum weighted F1 score of 69.73% using XLMR. In future, we have planned to include more classes such as love, hate, and stress. Text with sarcasm or irony or mixed emotions should also be included. We should also increase the data size by including more data in the corpus. Ensemble of transformer variants can also be implemented to compare with our current work. Thank you for listening to me. Thank you so much.